Thank you very much for the nice introduction, and hi everybody. I'm very happy to be here in my first RuhrSec and having the honor to close the conference today. My research area in general is usable security and privacy, so I'm working on human factors, and as you know by now, one of the topics that keeps me excited is user authentication. So how can we improve the situation that we have nowadays that you can clearly see in this image? How can we make it easy for everybody? And yeah, before starting with how to use the brain for this purpose, I just want to say a few words about the problem that I think is very relatable to everybody. So basically, we have to prove our identities constantly to access services, to access devices every day in many different, at many different points in time. And the dominant form of doing so is by means of passwords and usernames, which means that we have to remember long, sometimes complex secrets, and then input them in these devices with the difficulties that it entails. And it's clearly not usable. We have to deal with so many passwords nowadays, and even more after the pandemic and all the new services that we started using. We cannot cope with this load cognitively. And passwords come also with security problems. So they have been broken in many different ways, cracking by different types of malware, by social engineering. And we have seen also the costs of having to reset passwords in a previous talk, right? So it's not a surprise that through the years there have been several initiatives coming from companies, coming from industry, trying to kill the password, trying to find a better way. But the reality, what we see, what we do every day is that we are not there yet. And there are several reasons for that. The two most important ones are, first of all, inertia. It's very difficult to move on from a solution that is so widely deployed that in the end, yeah, it's easy to deploy, and everybody knows. And then another more interesting reason from the perspective of research is that we are failing to find alternatives that are better. And so let's take a look at alternatives. What are the possibilities there? What is in the landscape? When I want to prove my identity, I can do it by something I am, something I know, or something I have. The something I am refers to biometrics. Biometrics can be, there are more traditional biometrics, typically based on physical static characteristics like iris or fingerprint, but there are also more modern biometrics that are typically focused on how you do something, and this how you do is individuating enough to prove that you are a legitimate user. So the way you walk, that can be sensed with your smartphone, the way you talk, the way you type on a keyboard can be enough to yeah, tell that you are in front of the computer. Then in the something you know category, okay, we have passwords, and we have other secret-based alternatives like pins, also very common, and patterns. And in the something we have category, we deal with tokens or smart hardware that we can use to authenticate, like smart cards and smart tokens in general. And if we look at them from the point of view of usability, we have seen it before. For example, there are two main branches. One stream of research focuses on reducing the load of managing passwords. So basically, we have software that can store, generate, and autofill passwords for us. But these lack adoption right now, and they come with their own usability problems. There is a lot of research at the moment showing that people don't use password managers efficiently. So for example, not using the password generator, but using their own passwords just to be sure that they can remember them if they are locked out. And then we have single sign-on that we have seen in the previous talk that also comes with some vulnerabilities, and in any case, there is no universal provider, and the problem of having multiple passwords in the end remains. The other stream of research that is trying to focus on usability is related to this new novel biometrics, and it comes with an important characteristics, which is that you can implicitly sense the user. So you put a wearable and you monitor signals coming from the user body, and that can be done without any additional effort, which is very attractive. If I don't have to make an effort to get security, that's the dream. And also from a security perspective, what we get with this type of biometrics is that you can get the user authenticated through the whole session. So not only one-time authentication, and then you get an adversary in the middle hijacking the session, and you cannot check for that, but throughout the session, you can detect it if there are changes and block the computer or the service accordingly. And in this world of possibilities, I decided to focus my research on brainwave-based authentication. And I'll tell you why. So first of all, definition. What are brainwaves? Brainwaves are electrical signals produced by our brains, which can be recorded and measured. Here you can see an example electroencephalogram recording. The first recordings were conducted in Germany by a psychiatrist, Hans Berger, in the 1920s, and these were the type of machines used at that time, so bulky and meters of cables to get the readings. He described brainwaves based on recordings conducted on his own. I guess it has been always difficult to find participants for experiments. And he observed also that there are different rhythms. So we have high-frequency brainwaves that are present when you are engaged intellectually, when you have focused attention, and we have slower, low-frequency brainwaves that are more present when you are sleeping, unconscious, or relaxing, non-attentive. So we know what are brainwaves, and the important thing, if we want to use them as biometrics, is that brainwaves have distinctive features. These features can be related both to physiological factors. So if you see here, this is a human brain, and you see different foldings and curves in the cortex. This contributes to having a different waveform. So my brainwaves are going to look different from any other human based on these structural differences, right? But then there are also behavioral factors that impact the brainwave shape. And these are related to how we process and react to information. And for this, I want to do a small experiment with you. I need your collaboration here. So basically, I need your brains, eyes, and hands. And this is what we are going to do. I'm going to show you a sequence of images. And when you see the logo of RuhrSec, I want you to clap, just one single clap, OK? Let's do it. This doesn't count. OK, let's. I play the sequence. When you see the RuhrSec logo in the sequence, you clap. OK, nice. So you have seen that we didn't hear a single uniform clap, but there were different timings, different pressures. It was not a standard. And OK, in this process, there is more involved than just the brain, also the coordination. But it nicely reflects how different we are in processing and reacting to stimuli in our brains. So we have both physiological and behavioral components affecting brainwaves and making them individuating. And besides that, there are other advantages of using brainwaves as biometrics. The first one could be that they are not observable. I cannot look at you and see what is your brain activity, whereas if you are typing your PIN in an ATM machine, I can overlook it. Or I can recover a fingerprint from a surface, or I can use your face from a video and use it to fool a face recognition system. But brainwaves, at least by now, are not observable, so that's an advantage. And then, and coming to this usability advantage, they can be implicitly sensed. So in the past, there were these big machines, but now we have better tools that make brainwaves easily read. There are two categories of devices. One type of devices are medical-grade electroencephalogram readers, like the one in this picture. And then we also have consumer-grade electroencephalogram readers. The main differences are, for the case of medical-grade devices, this is the type of technology that we want to use for diagnosis because they are more accurate, right? But they are also very expensive, and they are cumbersome to set up. So it requires a trained person, and it can take up to an hour to wear this full set of sensors. And I guess you don't imagine yourself using this for accessing your smartphone. But on the other hand, now, since 2007, we have consumer-grade electroencephalogram readers that look even aesthetically nice. They are cheaper, ranging from 100 to 700 euros, and they are easier to use. You can just wear them and start recording in many cases. But, yeah, of course, the counterpart is that they are less accurate. And most of the research so far, trying to understand if it's possible to authenticate users with brainwave activity, has been performed with these medical-grade devices. But now we have many possibilities. So not only this one that I'm showing you here, but for you to have an idea, there are different neuro headsets in the market, including some a bit weird to wear in public. Then we have some more fashionable. We have others that are kind of discrete. Here we have in-ear sensors that resemble the type of things that we can wear normally. And there are even virtual reality vendors, including EEG sensors in their products. So there is a whole landscape of neurotechnology out there. And because of this, we see that it can be a more plausible possibility to have authentication based on brainwaves. So we wanted to explore this possibility, and we set up two research questions. The first one, is it possible to achieve accurate authentication with consumer devices? And since it doesn't matter if a security tool is secure, but you have to take also into account the human factors, we also wanted to understand how usable, how accepted would be this kind of technology for end users. And with these two research questions, yeah, we started conducting our research, and this is published in USENIX Security 2021, and it's joint work with my colleagues Thilo Habrich, Karen Schulze, Christian Becker, Thorsten Struve from KIT Castell and University of Mannheim, and also what I'm going to present here includes additional experiments by one of the PhD students that I'm supervising. So let me tell you about the methodology, how we tried to answer these research questions. So we designed a pipeline for a biometric system that follows the standard components. So first of all, we have to generate, and this is important, brain activity that can be used for authentication. And we measure these brain reactions with consumer electronic device using 14 sensors. So let me tell you about the generation process. We are not measuring the continuous EEG signals, the time series from the users, or we are not using the whole continuous signal. But what we do is the following. So in our experiment, the subject is seated in front of a computer, and we present some stimuli on the screen, and once these stimuli are perceived by the brain of the participant, we get a reaction. And this reaction is time-locked. So after the stimulus presentation, some milliseconds after, I get a peak, I get a specific wave that peaks and then dies. And we are going to take only this part of the signal because it provides a better signal-to-noise ratio. And we thought that would be convenient for the case of using electronic devices that have worse sensors. So we input these pieces of data to our biometric system which contains the following blocks. We start with signal preprocessing, basically to filter out the noise. Artifacts that can contaminate the signal because, for example, if you blink, you get signals that are higher and you have to filter that out, electric noise, and so on and so forth. And then we extract features that are relevant for classification, and we use a classifier to detect if the user presenting these brainwaves is a legitimate user in the system or not. To evaluate the system, we consider a zero-effort attacker, so basically claiming the username of the victim and just presenting his own brainwave measurements to the authentication system. And we measure performance based on the standard metrics, the percentage of imposters accepted in the system, false acceptance rates, and the percentage of legitimate users that are being rejected, the false rejection rates. We managed to recruit 52 participants to record their brainwaves. The sample is skewed towards males and young people. This might seem a small sample, but in comparison to the experiments conducted in the literature with this type of devices, it's quite big. And we tested 5 different authentication tasks and compared them comprehensively from the performance point of view, but also from the usability point of view. So let me say some words about the usability. After we measured the brain data of the users, we asked them to fill a questionnaire, and there we collected both quantitative and qualitative feedback. Quantitative questions were focused in understanding how enjoyable or how much attention was required, or if users were willing to repeat these tasks on a daily basis for authentication. And then we analyzed the difference with hypothesis testing. And for the qualitative part, we wanted to get richer insights, so what is working, what is not. And we asked participants about which problems they envision in this type of system and what would be improvements that they would like to see if they use this technology. And then we analyzed this with qualitative content analysis techniques. And before going into the results, I want to tell you a little bit more about how these generation tasks, these authentication tasks look like for the end user. How do I authenticate with a brainwave-based system? And one example of the tasks, of these 5 tasks, was a user-selected image. This task is built on a neuroscience paradigm that is called the oddball paradigm. This says that if I show a user a sequence of standard elements, like these gray rectangles in the series, and in between them, I show something that is different and that is rare in occurrence, the red rectangle in this case, then my brain will react with a waveform that peaks around 300 milliseconds, and that is positive. So this is called the P300 event-related potential, and we decided to exploit this paradigm to create our authentication task. How did we do it? We asked the participants to select an image that was their kind of password. And then we showed them this selected password image in between a series of random images. And in between them, their chosen password was infrequent. So we followed this oddball paradigm. What the users see is something like this, right? And after this sequence, they automatically get access to the system. This type of task was based on attention, and there are other type of tasks that we designed based on semantic processing of images, but also of textual stimuli. To give you an example of this other type of tasks, I want to show you the sentence task that we designed, and this is based on establishing a semantic context and then violating it. What does it mean? So I will show you a sentence that is congruent, like I take my coffee with cream and sugar. And this is normal. Then I take the same sentence and I say, I take my coffee with cream and dog. which should not be semantically reasonable for a person. And therefore, to process that difference, we get a reaction in the brain that in this case is of a negative form and peaks around 400 milliseconds. And this is called the N400 event-related potential. So the other type of response that we were looking for. And with this, I think I can move on to the results. We tested, as I said, five different tasks. The image one, that could be either a selected password, selected image, or an assigned one. We tested the incongruent sentences, and just to briefly describe the other two, the worst task was based on priming the user. So this is similar to the cache operation that we saw in the previous talks. So basically, if I show you a video of cars driving, then I show you words that are related to that context, car, truck, road, because that information is directly available to you because you have been primed, you react differently and quicker. So we use that kind of task for that. And the other one was showing familiar and unfamiliar faces. If I show you a set of familiar faces, you preload in your brain some mechanisms that allow you to identify this familiarity. If in between I show you something unfamiliar, you have to inhibit that knowledge, and then you get a different reaction in the brain. So what were the results? We tried to benchmark several classifiers, and we compared them to obtain that the best result was with the image-based tasks. Looking at the operating curve, this gets us a result on an equal error rate, so that's the point where the false acceptance and the false rejections are the same. If you move, then you trade one or the other. So our equal error rate was 7.2%, and how good is that? It improves related work significantly. With consumer devices, up to now, we only get between 22 and 26%. And it is on par with results obtained with medical-grade devices. So that's good news. And in any case, we don't work with equal error rates when we use authentication, but what we want is a low false acceptance rate. We don't want imposters accessing the system, at a reasonable false rejection rate. We don't want to lose usability either. So one common point is false acceptance of 1%, and at that point, our false rejection is on the order of 22%, which means that there is room for improvement. This 1% is good for low security applications, but if we want to use this type of authentication in high security applications, the requirements are more strict, like 1 in a 100,000 false acceptance rate. So here again, there is room for improvement to get more accurate systems using brainwaves as authentication. And those were the main results regarding performance. There have been other learnings through the process that I also want to share with you. And these are related to the number of channels. So this headset had 14 channels, and we were wondering with how many channels can we get still reasonably good accuracy. And so we started selecting channels randomly, 2, 3, 4, 6, until, and measured the equal error rate for these random combinations. And what we saw is that after 9 channels, the equal error rate kind of stabilizes. So we can get reasonable results with less channels, which means that we can have designs that are more usable for the user heads. Then we also tried something else. We saw that in the literature, the results that were reported included the attacker's data within the training of the system, which means that the model can learn something. So we decided that that was not realistic enough, and if we want to understand practical applicability, we should also test for imposters, for attackers that are not seen by the training process. And we call that open set evaluation, and basically, as you can see now, all the equal error rates degraded when we tested this case. And so it's really important to test these cases also in further research. And now the second part. So we have seen the security and the performance, and what about the usability? What do users think? Regarding the quantitative part, what we saw is that users prefer visual stimuli. It's nice to look at images, but they don't want to read or process textual stimuli. And this was statistically significant between different tasks. For the qualitative part, we code the results, and if I have to summarize the key most important points, I would say that users called frequently for simpler headsets. We use this headset here, which is, as I said before, 14 channels, and it's not straightforward to use because the sensors need to be moisturized. So you have to hydrate them before using it, and if they are not correctly hydrated, then the connection is not good. And then you have a connection checker to see which sensors make good contact or not, and if you have a lot of hair, that can be also challenging. So they were calling for simpler headset, and this is an important thing also related with the number of channels that I mentioned before. With 9, we can get also good results, so maybe also simpler designs. The second point raised frequently was that authentication must be quick. If I need to look at a lot of images to get in my system, then typing a password is not that painful. And many people were concerned about the stability of brainwaves. So what would happen if I'm tired or stressed, if I had caffeine? Will I be locked out of my system because it doesn't recognize me? And the last point, also very interesting, is privacy concerns. Participants look at privacy from 2 perspectives. They were concerned with mind reading. Will the service provider be able to get access to private information, to my thoughts? And also from a different perspective, can I be manipulated with the type of stimuli that I'm being presented? So these are actually very, very valid concerns. There are works as early as 2012 in USENIX Security that show that you can use the stimuli, you can manipulate them to use brain-computer interfaces as side channels to leak secret data. And they show that you could learn, for example, if somebody knows a person, or what is the bank where they have an account, or even some numbers of their PIN, or at least reduce the entropy in trying to get that secret. So very valid concern. And with this, I want to come to the wrap-up of the talk. And the main takeaways are that we conducted a comprehensive analysis of stimuli response brain-based authentication, showing that there is feasibility to do so with consumer devices. And we also collected during the process insights from the people that can be useful to design future prototypes. What we observed when trying to compare our results with other research is that there are several problems in this comparison. Many works don't report a lot of metrics. They just report, for example, one data point or the accuracy, which is not meaningful in a binary classifier for authentication. So you cannot really tell if one system is better than the other. And also there is a lack of data sets, publicly available data sets, where you can apply your mechanisms and try to reproduce and benchmark your algorithms. So to contribute to this effort, we also published, and you have it available if you are interested, the data set of our participants, brainwaves, and also the full experiment design that can be run with the stimuli presentation. Of course, we don't see this as an alternative or universal alternative to passwords. There is a lot of work to do. And in any case, we think that this is applicable in special cases. So for example, imagine hands-free scenarios. I'm a factory worker, I need to conduct some tasks, and I also need information, to access information to do this work that requires me to access service. And I might be wearing this type of headset already for cognitive load detection, so the machines can adapt to my pace. This is a real use case. And since I'm using this device, that can be leveraged for authentication. That seems natural. And then there are, for example, virtual reality scenarios. Their passwords are completely non-convenient, and there is no gold standard for virtual reality authentication. So with these new vendors integrating the sensors, that could be also a seamless possibility. Future directions, where to move from here? Well, we need to, and we are also trying to work on improving the performance, how to get false acceptance that are lower, and then testing robustness. How will this system work in different sessions? Will it be stable? Then the usability evaluation that we conducted, and there are no other usability evaluations with users, relates to perceived usability of an imagined system, but they didn't interact with a real prototype. We collected the data, then we ran the algorithms, but we lack this testing of being authenticated real time with a prototype, and ideally not only in conditions, in lab conditions, but also in the wild. One such path to improve performance is applying or fusing multiple BIOS signals, for example, including eye tracking data, which can also be collected in a non-invasive way with the brainwave data to improve, to get more cues about the user and improve this performance with this accuracy. And I think one of the most important topics for the future, not only for authentication, but for any type of application using neurofeedback, we need to think about privacy. There are a lot of things that can be inferred from your brain activity based on clinical literature. They correlate to drug addictions, to emotional states. You can predict gender, age, or things that you wouldn't like to disclose to a service just for free, and that you might not know that this happens. So I think it's very important to research on privacy-preserving technologies for brain-based applications. And with this last item, I would like to finish the talk. I hope that your brainwaves are not in the alpha low frequency and that you learn something new. Thank you very much, and I will be happy to answer your questions.